So thank you again. I would also like to thank the organizers for giving me this fantastic opportunity to talk to you today. So thank you very much, and it's been a very nice conference so far, really well organized. So the title is there. What I'm talking today is basically droplets and superfluids, and it actually turns out that you can also make droplets out of superfluids, but that's another topic for another day. But let me start by making a little journey. So unfortunately, we couldn't meet in Lisbon. That's a real shame. I was looking forward to flying over there, but instead I can at least fly you all to Australia. So let's do this. This is a very quick flight. Trust me, I've done this many times. It doesn't take long at all. So here we are. We have arrived. So once we are here, I would like to acknowledge the Wurundjeri people of the Kulin Nation, who are the traditional owners of the land where our Swinburne campus is located here, and pay my respect to their elders past, present, and emerging. So this is the slide of acknowledgements. So I'm getting for the past 10 years or so, I've been funded by the Australian government and the taxpayers, and by corollary, I'm also partially self-funded researcher, as I do pay taxes. We've got this new Optical Sciences Center, so I'm leading this Enion Technologies group within the center, and these are the three main research programs that we are interested in at the moment. I would also like to thank my colleagues and collaborators, and in particular, I would like to highlight Rahil Valani, who many of you know. Rahil recently finished his PhD and is now continuing his academic career at the University of Adelaide. And I would also like to thank John Bush for his help in getting us introduced into this new research field for us. So thank you for that. Okay, so the outline of the talk is here. So as I mentioned, I've got two parts, and at the outset it looks like they are seemingly unrelated, but I hope to convey to you that there are some very clear mathematical links between these things. So I will start by giving you a very brief lab tour, since you are all now here on our campus, so we can go and have a look in the lab. And then after that, I will talk to you about this emergent physics in these superfluids. So here are the list of the papers that you may want to consult if you want to find more finer details. But let's start. So this is the way the lab looked when I arrived. As you can see, there's a lot of oil on the floor. The room used to be a mechanical workshop that explains it, and when the trains drive past our campus, you can almost see Faraday waves on this whole surface here. But thankfully, our university is treating me very well, and so they gave me a new floor, painted the walls, even gave me my very own airline. It doesn't have wings, but at least it gives me a continuous flow of compressed air. And perhaps the most importantly, there is a nice new air conditioning system that will give me 0.5 degree centigrade temperature stability in the laboratory, which will be very useful for these droplet experiments when the viscosity of the fluid is temperature dependent, and therefore the Faraday threshold is also temperature dependent. So that's nice. A little bit later, now you can see there is an optical table, weighs about 1/4 ton on top of those 4 posts, and underneath you see the favorite workhorse, the R2D2, as I call it, the electrodynamic shaker that makes the waves. And one particular thing that I want to mention about this setup is that we've got actually a very nice way of leveling this experiment very, very precisely. As a matter of fact, what we do is we tilt the whole table by adjusting the air pressure in the legs of this table, and it is very easy to align the whole table very precisely within the thousandth of a degree. As you can see here, I left a little bit of tilt in the x direction just so you can actually see that it is measurable. But this is what we do. So the experiment is fixed once and for all, and then we just adjust the whole table, which also provides the vibration isolation from those trains that drive past. And this is getting quite close to what it looks like at the moment. So the shaker is underneath there. We've got the air bearing stabilization that removes the unwanted horizontal vibrations, and there's the fluid path. Got top view imaging and side view imaging there behind this pillar here, looking in an angle into the fluid path, and resolves the high frequency vertical vibrations. So this basic setup here is the model based on the Harrison-Bush design, and likewise the droplet generator is also from the same people, the same basic design going on there. Another feature here is a two-axis linear stage that we can computer control. So that enables us to deposit the droplets on demand anywhere on this 2D plane, which will be very useful for multi-droplet experiments. Printing, I call it a droplet printer. We can print any patterns of droplets with this. So once things start getting going, of course, what do you want to do? You want to make waves, and in particular, you want to make Faraday waves. Here's a picture. Here's the movie. I won't play it very long because it's going to give you a headache, but just want to show you. It's quite nice to look at these movies, as you all know. And once you've verified that you can make Faraday waves, then you, of course, need to make droplets as well. So, for example, we can make double droplets, and we can make little satellite droplets, and of course we can also make single droplets on demand. But I just want to, I just love this movie, so I'm just gonna show you. Have a look at the big droplet on the left as it falls, and look at the little droplet above it that doesn't seem to be falling at all. This is so much fun looking at this. It's a really good problem to give for first-year students, and I always give them the hint that to explain what's going on, you do not need to resort to anti-gravity. So that's the only tip. But talking about gravity, we can actually test gravity with this experiment, as you can see. So MATLAB has been mentioned a few times, so I mentioned it again. So this is the best parabola you can make with the MATLAB, and as you can see, the droplet is fairly closely following the parabolic path, so it looks like gravity is all good. And the final statement about this slide I want to make is all of these droplets that you see here do indeed fall towards the center of the gravity, center of the Earth, despite of the fact that we are on the southern hemisphere here in Australia. Okay, so once you've got droplets, you put them on the fluid, they start bouncing and walking and doing their dance, and these videos, could keep me entertained for days on end. I could just, keep watching this for the rest of the day. They are it's just beautiful to watch the dynamics going on here. So that's basically, roughly speaking, the current status of the experiment. Is getting very close to, I still need to do a few bits and pieces, integrate the computer control and few little electronic additions, but very soon I hope to be able to start doing real experiments on this. And I've got a very, very long bucket list of things that I want to do. So this is just a very tiny starting point. What is on the menu, and so to give you an idea, so here these fun forth and forth and back and forth type super walking stop and go behaviors that you can see. The left-hand side droplet there is it keeps moving, it stops, it moves, it stops, it moves, it stops, it knows where it's going, it's determined, The other droplet on the other end is a little bit confused. It doesn't quite know whether to go one way or the other, and so it just keeps going back and forth. Okay, so I'm now going to switch gears, and we are going to leave the laboratory and discuss another kind of fluid. So the first part there was discussion on these classical fluids, and the second part I will be talking about quantum fluids. So we also have got at Swinburne University, my neighboring laboratories, that they do make these superfluids that I'll talk about actually in the laboratory. So we've got experiments making Bose-Einstein condensates and superfluid Fermi gases. So mathematically, how do these two things link? So here as you've many times already seen, the top equation here is your Navier-Stokes equation for incompressible fluid, one of those forms. And the equation below it is the nonlinear Schrödinger equation in the cold atoms community that I've been spending most of my career. It is called the Gross-Pitevsky equation, but mathematically it's the one and the same thing. Obviously, dear child has got many names. Mathematics is the same. So this is the hydrodynamic form of the Gross-Pitevsky equation, or the nonlinear Schrödinger equation. And how do we link these two? Well, one thing which is an experimental fact is that these superfluids are irrotational. So that means that we basically need to throw away the curl term here. And so you can imagine a classical fluid that is irrotational, that's fine. Or you can approximate the rotational part in the superfluid, which is there is curl, but the curl occurs only at discrete delta function points called quantized vortices. And so it is possible for the superfluid also to rotate. So that's the connection there. Obviously, we need to get rid of the viscosity. Superfluids are by definition non-viscous fluids. So if you throw away the viscosity, it becomes a superfluid sort of. But again, we can get away with this by considering, for instance, turbulence in the inertial range, in which case you can throw away the viscous effects in the inertial range and the kinetic energy wins, and you can neglect the viscous effect to a large extent. Or you can supplement the Gross-Pitevsky equation with viscous effects that actually are there always. There's sort of a so-called mutual friction whenever you've got vortices. The vortices interact with the non-superfluid part of the system and gives you effective viscosity. And finally, here's the term that has already appeared many times in this conference and many other places. Again, in the cold atoms community, this term is called the quantum pressure, and it is there's nothing mysterious about it. It is simply just the density gradient of the superfluid. So the fluid has got density variations, and those density variations cost you energy, and this term caters for that. Of course, both equations also have got the continuity equation supplementing, but that's the same for both cases. So that's basically the link there. But numerically, using the hydrodynamic form for the superfluids is very cumbersome. The reason is that you need to impose somehow the irrotationality condition, and that is not very easy to do numerically. So it is far easier to actually solve the nonlinear Schrödinger equation or the Gross-Pitevsky equation directly as such. So that's actually pretty straightforward, and that can be done very easily. And so here I show you one simulation. So this equation is what we are solving numerically, and I'm showing you here below what it looks like. So let's have a look. This is the dynamics. What you see here is these blue and green dots, and they are vortices. They're like your bathtub vortices circulating one way or the other. So two left-handed and right-handed circulating vortices, and they move in this fluid. And the lighter stuff in the background is simply the density of this fluid. It's actually gas, these Bose-Einstein condensates are in gas form, and this is the superfluid that is sloshing around. The density is moving there, and you see this wonderful hydrodynamics, the superfluid quantum hydrodynamics going on here. I'll return to this movie later, and I'll tell you a different story for the same facts here. But I just want to highlight and emphasize once again that what you just saw there is an extremely good mathematical model for real laboratory superfluids that we are also studying. And here these are real experimental images of those Bose-Einstein condensates. For example, here you see the similar sort of fluid density, and these dots there are the quantized vortices that are of the order of 1 micrometer in the spatial scale. I can't help myself but showing you this this pair of images. This is just the mind-boggling. Have a look at the scale. There's a 25 orders of magnitude scale difference between these two images. On the left-hand side, you see a galaxy. It's got some name and some number. On the right-hand side, you see a Bose-Einstein condensate, a superfluid, BC. I gave it a number based on this year because the image appeared this year on the archive. And, well, you could say that, well, okay, they look the same, but actually it's far more deeper than just looking the same. On the left-hand side, presumably this thing used to be in some sort of a spherical gas cloud, and somehow it got some angular momentum and started rotating and evolved into this sort of shape that you see at the moment. Nice. On the right-hand side, this is also a gas of atoms. There's about 10,000 to 100,000 atoms in this image. And it used to be a sort of spherical cloud of atoms until the experimentalists at the Swinburne group at MIT made it rotate deliberately. They gave it some angular momentum, and then they waited for a little while and took an image, and this is what it looks like. So 25 orders of magnitude difference in scale, and the dynamics is giving you practically the same kind of hydrodynamics. I put this telescope here. You look up in the sky and you see something like this. You look in the other end of the telescope and it becomes a microscope and you see something like this. Have a think about that. Okay, so very briefly, I want to now digress and put in a one slide summary of the present understanding of our universe. So once upon a time, there was a phase transition. A special kind of superconductor emerged, and there's a lot of excitations, all sorts of topological defects in this superfluid superconductor, and it's been expanding ever since. And this superconductor is, of course, our standard model of particle physics. I'm not writing the Lagrangian here; it wouldn't fit on this slide. I'm just giving you the symmetries. And these symmetries determine they've got representations, irreducible representations of these symmetry groups, and they correspond to the particle, the elementary or fundamental particles that we have discovered, such as electrons. So it's a quantum field theory of this special kind of superconductor. On the other hand, we've got the Einstein's field equations that are nonlinear classical fields, very compactly can be expressed in terms of the Einstein-Hilbert action here, where R is just the curvature scalar, and you've got the determinant of the metric tensor in four-dimensional space-time, and kappa is the Newton's, essentially Newton's gravitational constant. So this is the state of the matters, but the issue is how do we marry these two things? We've got quantum field theory and some classical field theory, and they don't seem to go very well together. And so there's major conundrums of the modern physics. There's the rabbit is barking there. What is quantum gravity? And the duck is quacking for dark matter. And obviously this is wonderful once these are sorted out. But that's the current state of matters. And for the rest of my talk, I'm going to talk to you something completely different. But I'm talking about these superfluids. I'll go back to these Bose-Einstein condensates, which are superfluids, and we take a viewpoint over one superfluid that forms in a phase transition from thermal cloud of atoms, for instance, to a superfluid cloud of atoms. And in this phase transition, particles are created. All the properties of the superfluid emerge, the collective degrees of freedom, and so on. And so this is the analog universe model, and there's a couple of nice references that you might get started with if you have not heard about this before. So this is what happens in laboratory, and these things can be studied in the laboratory. So a bit more mathematically, so this equation here is nothing but the energy functional of the Gross-Pitevsky equation, that is the nonlinear Schrödinger equation. So if you take a variation of this energy functional with respect to the fields, you'll just get the Gross-Pitevsky equation. All good. The second line here is identical. This is mathematically identical equation. All I've done here is to give them the new names for old things. So obviously nothing happens mathematically. So what I've done here is I'm calling the superfluid dark matter. I'm calling the excitations of the superfluid, specifically the quantized vortices, I call that normal matter. I'll call the chemical potential of the condensate the dark energy, or the cosmological constant, if you wish. And I call the kinetic energy gravity and electromagnetism. And I split that term into two parts. The second part is the density variations, the quantum kinetic energy of the fluid, and that gives rise to sort of a dilatant type of general relativity, which I'm not going to talk to you much about today. I'm talking to you more about the first part, which is just the half rho v squared of the fluid, and that gives rise to this effective electrodynamics in this system. So the two major key points about these BCs, these post-condensates or the superfluids, is first of all, the excitations in these fluids are photons. So they're phonons, or which become the photons in the real universe, but the phonons are the sound waves that propagate in this fluid, and they are just density perturbations that propagate as waves. This is an excitation spectrum, the so-called Bogoliubov excitation spectrum of those phonons, and this has been verified experimentally and well understood theoretically. And the key point here is that you have got a linear spectrum at low momenta, and it turns into a quadratic spectrum at high momenta. So at the very, very low energies, the excitation spectrum is linear. This linear part corresponds to these phonons, that sound waves that are traveling in this superfluid, and that gives rise to this acoustic metric description originally due to Unruh. The second key component of these superfluids is the particle content. And the particle content is just these quantized vortices. So in this scalar Bose-Einstein condensate, the order parameter is described by the U1 symmetry, and the only particle that exists in this system, this topological particle, is a vortex, and it's anti-vortex. So these are the electrons of this superfluid, and the vortices are exactly in the same way as in standard model. The standard model particles are the representations of the symmetry groups. So are the vortices of the superfluids. So we've got the potential flow of the superfluid around these singular points, and those singular points are these charged particles called quantized vortices, and their charge is given by Planck's constant divided by the mass of the particle that formed the superfluid. L is an integer, and typically you can just take to be 1. So how does this map on this electrodynamics? So we have phonons, sound waves, and we've got particles, the vortices. The electromagnetic field is nothing but the motion of the superfluid. So the electric field is simply the gradient of the spatial phase. Magnetic field is the temporal gradient of the phase. In other words, the electric field emerges when the superfluid is in motion. So the flow of the fluid gives you electric field, and the mere fact that you've got atoms in the energy in the system gives you a magnetic field, and you can define these sort of vacuum constants to get the speed of sound. And the matter content, the current here is a current of vortices, it's flow of vortices, the velocity field of vortices, and the density of the vortices, and the density of the vortices is nothing but the vorticity of this superfluid.
Tapio,
So,
Tapio, just
yep.
to remind, we have used 25 minutes, so just so that
yes,
you know.
yeah.
Okay.
I've got maybe 3 more slides, so I'm on time.
Just so you know, no problem.
Perfect, thanks. So here are the Maxwell's equations. There's nothing surprising about that. But the perhaps surprising aspect is that you can actually derive all of these equations directly from the nonlinear Schrödinger equation. That is the Gross-Pitevsky equation. Okay, so the mapping here, so the caveat is we are in 2D. So we are considering two-dimensional fluid. The Gauss's law is nothing but the quantization of circulation. Okay, so the second equation is triviality because we are in 2D. The magnetic field points out of the plane, and we are the fluid lives in the 2D. So that's fine. No magnetic monopoles in this universe. The Faraday, Faraday's law is just the continuity equation, and the Maxwell-Ampere law is Euler's equation. So this is actually mathematically, you can derive these. This is not just like I'll just put them out there and I pretend that this is something. You actually derive these equations. And likewise, the Lorentz force law is just nothing but the Magnus force in the fluid dynamics. So this is basically the mapping, and you can derive this mapping. And now that we have got this viewpoint of the superfluid, I'm going to play this movie again, and I'm giving you a different perspective. So you can either take this quantum turbulent perspective, which is superfluid in motion, chaotic dynamics of these vortices, or you can now look at these blue dots are electrons. You know, electrons are always blue, so they're electrons. So the green ones have to be the anti-electrons, that is the positrons. And I play this, and you're seeing the quantum electrodynamics here, where blue and the green charged particles can annihilate and emit photons or the sound waves in this system. And you can also create pairs. The vortices and anti-vortices can be created. There's pair creation processes going on in this movie. You see the sound waves, that is the photons flying around through here, and the density variations are occurring all over it's just the superfluid density that's varying there. But in this system, it is the dark matter. It is the gauge field underlying this matter content, and the matter content is just these blue and the green dots that you're looking at there. So this is the perspective that you can take. Of course, nothing changes. This is still what happens in laboratory experiments. It's just a different viewpoint that you might want to take for this, because you can. So I'm going to summarize my talk with these 3 points here. So I told you a little bit about the development of the new laboratory at Swinburne University that is going to do some droplet experiments. And then I gave you this viewpoint on this quantum electrodynamic viewpoint of this two-dimensional superfluid dynamics. And what I did not have time to tell you about is the fact that you can also create what is known as spin or Bose-Einstein condensates, where you need to take into account the spin degree of freedom of the atoms, and you get multi-component order parameters, and those superfluids have got a lot more interesting particle content, lots of different types of vortices, including non-abelian vortices that basically give you an effective QCD type of phenomena in these superfluids. So that's quite a lot of fun. There's lots of interesting things you can do with this. So the point here was that you can take the superfluid in the laboratory and view it as a little mini universe of its own, and the entities that live in this superfluid are quasi-particles that formed in the phase transition when the superfluid was born, and all the laws of physics, if you like, in this analog universe emerged at the moment when the phase transition to this superfluid phase occurred. So there's turtles. My time is up. If anyone wants to know about turtles, they can ask me after the talk. Thank you very much for your attention.